So in our last video, we looked at what acids and bases are, and we looked at the idea of how acid-base reactions work, that they work to neutralize each other. So there's a very specific way of analyzing acids and bases that we're going to talk about in this video. So you may have heard the term before, depending on what you've looked at with this technique so far, and it's called a titration. So titrations, in this class, what we're going to be looking at is what you do is you have a substance of a known concentration there didn't need to be a comma. Not that you care about my English, but there shouldn't be a comma there. So it's just a substance of a known concentration that is added to another substance of an unknown concentration. But not just the fact that it's an unknown concentration, but it's to learn the concentration of that unknown. So the reason this sounds kind of vague is because titrations can be different things. It doesn't just have to be acids and bases, although that's all we're going to deal with in this class, or at least right now. So the main way we're going to do this is by taking an unknown acid where we're not sure what its concentration is, and then adding a known base, or doing the reverse, taking an unknown base and adding a known acid to figure out its concentration. So the idea is we've got a flask, and then this flask will have a known volume. Like let's say we want to know, we think that we've got a river, and we've taken a sample out of it, and we know that river we have reason to believe it's slightly acidic from some test we did, but we want to know how concentrated the acid in the river is. And we have, let's say it's some water sample we know was contaminated. Like, oh gosh, Dr. Leslie's chemistry class accidentally spilled some HCl here. They weren't supposed to do that. How bad of an impact did it have on this water supply? So let's say it's a lake instead, because a river, it would just all wash away. You could still have contaminants in a river, clearly, but for the exact scenario, it wouldn't make sense as much. It wouldn't stay all that long. Now, if you drop something in the lake that made constant changes to the pH of it, yeah, then it would still do it. But yeah, so we've got a lake. Lake by here, we accidentally spilled some HCl in it. Oh gosh, what do we do? So we want to know what the concentration of the whole lake is. So we've got a whole lake, our lake, but Dr. Leslie is like, oh, we don't need to test the whole lake. What we could do is I'll get a sample. And the very well-drawn Dr. Leslie and his stick figure self takes a sample back to the lab and puts it in this flask that is clearly not to scale. At least I don't think I have any flasks that are taller than me that I have to reach up to a ladder with. So we're going to assume a normal flask. So in it we have, let's say, 20 milliliters, or 20.0 milliliters. That's how much we put in there. And we don't know the concentration. We know it's HCl because we spilled it in there. So we know we have 20 milliliters of our HCl lake water. The concentration is, we don't know. So that equals big question mark. Oh, the question mark is behind my face. So question mark here. So what are we going to do? We're not going to change the slide like that. Eventually I'll stop doing that. So we're going to set up a titration setup. What we do is we have something called a burette. And we're going to add drops of a base. So this is going to be a base. Now we want to learn about the acid. So what we're going to do is we're going to add, let's say, 0.100 molar NaOH. And the idea is, as we add base, it'll react with our solution that's in our flask. And like we learned in the last video, that's a neutralization reaction. So what we'll do is we'll have some way to detect when the acid is gone. So when it's all neutralized. Now there are a few ways to do this. One would be to have a pH meter in there. So pH tends to be low when it's acidic, or it is low by definition when it's acidic, and we can watch the pH. As the pH goes up, once it goes past 7, it'll be a basic solution. Another way to do it, which is also prettier and more fun to do, is we can have a substance called an indicator. So what an indicator does is it changes color based on the pH of the surroundings. Well, technically there's some other ways you could, in theory, I think we actually worked on this with some people that want to know how to help students that were visually impaired or colorblind do a test. You could do it with a smell-based check. I remember working with some students on a project like that. But in most instances, it's a color change you're looking at least for acid-base indicators. So you add a substance in that's not going to interfere with the reaction, but that's going to change colors. The most common example, and the one if you did something in high school, there's a very good chance the one you did used a substance called phenolphthalein. Phenolphthalein is clear when it's in an acidic solution, and I don't remember the exact pH it changes at. I've used this a reasonable number of times. You've got big tables of these. You can look these up pretty easily. But it's going to change purple, or to a pinkish purple color, when it switches, when the pH goes up to a certain amount. So you pick one based on your acid that'll be an appropriate change. So you can get indicators that occur at lots of different places. So depending on the substance you're working with, the pH will change differently when you're neutralizing it. So in this case, we pick phenolphthalein. It works really well in this case for a strong acid, strong base reaction. And so we're going to add the base a drop at a time. And the second that substance changes color, it's fast. It goes from clear to purple. Now, if you're doing it really carefully, actually what you do is it starts to turn purple, then it'll turn clear again, and you have to swirl it, and then you get to just the exact point where it just turns purple, but it'll be there. Then you hit what's called the equivalence point. So the equivalence point, I lost my marker. There it is. The equivalence point is when you add just enough to neutralize everything. So just enough acid or base to neutralize. So this will depend on what you're working with. So if you have an unknown acid, it means you added exactly enough base to neutralize all of it. If you have an unknown base, it's just enough acid to neutralize all of it. That's the equivalence point. So the goal of this titration, at least in 1211, is just to find that equivalence point. You want to know exactly when you got rid of all the acid or base. And from that, you can figure out the concentration of the substance you're working with. So how does that work? Well, in our case, we're working with HCl, aqueous, plus NaOH, aqueous. And when we do that reaction, we form water, plus we form NaCl. So, at equivalence, all NaOH and HCl react. And it doesn't have to be exactly these two substances, right? It's whatever acid and base you're working at. So you have exactly enough to get this reaction to go. You don't have an excess reactant. You don't have a limiting reactant. That means if you know moles of one, you can find moles of the other. So for example, in this question here, as I'm pointing, it's up there. This feels weird. I'm trying to point up at it and I have to point like there, and that's not even getting to the question. My finger won't reach that far. But you can see the question above my head. So when you have exactly enough, then the moles of HCl will equal the moles of NaOH because it's a one-to-one reaction. You'll have exactly enough. So we said in this problem we were adding that the sodium hydroxide was our known concentration because that's the one we have. Then we have this HCl that we don't know what its concentration is. So what you'll do is you'll measure how much NaOH you need to add because we know we have 20 milliliters of HCl. So let's say for our problem, let's say it took 3.4 milliliters to neutralize it. So that's when we get the color change. So like if you were doing this in a lab, you're adding it a drop at a time. And the idea of a burette is like you can literally read it. It's got a volume and it tells you how much you've added. So you start with 50 milliliters or so in your burette, and then it starts at 0. And as you add it, the numbers actually get bigger and bigger because it's recording how much you've added because it's specifically built for this technique. And so then you finish, and then you check it. Oh, it took exactly 3.4 milliliters to change my substance to pink, and it stayed pink. So that means I got my transfer to work right. So I want to know what was the concentration of that HCl then. So what we'll do is we start with our information. We have 3.40 milliliters of NaOH, because that's the thing we know about. We know how much we added, and we know its concentration. We can't start with the HCl because we're missing both the moles and the concentration. You can't find both at the same time. So we've got to start with a substance where we know 2 of the 3. So here I know volume, I know concentration. Those 2 are enough to find moles. So we start by converting this to liters. 1,000 milliliters is 1 liter of sodium hydroxide. And then we know from our concentration that for every liter of sodium hydroxide, we're going to have 0.100 moles of sodium hydroxide. Now, We don't want sodium hydroxide, though. We want to know about the HCl part of the sample. So for the HCl, for every mole of NaOH, you get 1 mole of HCl. Please note, you have to do this step because it's not always 1-to-1. So for example, imagine if my pond had H2SO4. If you balance that equation, it takes 2 NaOHs to neutralize 1 H2SO4 because H2SO4 releases 2 hydrogens and sodium hydroxide only releases 1 hydroxide. So you end up needing 2 hydroxides to interact with those 2 hydrogens you're making. So it's not always 1-to-1. You cannot skip this step. And I say that because I think you get the right, about 70% of your cases or so, or maybe even 80% will be monoprotic acid, a base that just has 1 hydroxide. So it's easy to get into a pattern of, oh, I just skipped this step. Please don't. You miss the other ones and it avoids the logic of why does this actually work. So in our 3.4 milliliters, we've converted it to liters. And I realized that my L looks kind of like a 2. Let me make sure this looks like an L. Oh gosh, I'm trying my best here. So, liter of sodium hydroxide, switch to moles of HCl. So now that will give me my moles, so I can multiply all this out. And then I can combine that with my volume to find my concentration. So 3.4 milliliters divided by 1,000 times 0.1. So it's a pretty small number, which makes sense. We don't have a whole lot of moles. This concentration isn't going to be all that high. So we have 3.40 times 10 to the negative 4th moles of HCl. So to finish the problem asked us for concentration. So we want the molarity. So we have 3.40 times 10 to the negative 4th moles of HCl. And then we have to divide by the volume in liters. So they told us it was 20 milliliters. That's the same as 0.0200 liters. So if we divide by that, we're going to get that our concentration is equal to 0.0170 molar. That should be an M, not an N, for our HCl. So this means that our pond that we accidentally spilled some hydrochloric acid in is now 0.0170 molar HCl, assuming that there are no other acids in the pond or something like that. So we're assuming this is a simplified situation. We have 1 acid, and we tested for it, and now we know how much there is. So this is how we use titrations to do something productive with it. Now, this is not the only type of thing you can use for a titration for. You can test for things other than acids or bases. You just have to have some type of test where the goal is, I can add something that I know about to learn about something that I don't, and I can track it in some way, either a color change, something like pH, or just anything else I can measure that changes as I add this known substance. And that change has to be connected to the concentration. It can't just be, oh, I know it changes, but I don't know how it connects to concentration. That's what's making it a titration here that's useful. We're going to stick to acid-base titrations here, but it's not the only thing. You have other measurement techniques we can use. Also, if you go to Google information, like you want to learn more about titrations, understand that even if you're just looking through general chemistry materials, we have an entire chapter dedicated to acid-base titrations in 1212. So we're going to take this technique and go a whole lot further with it and get a lot more information out of it. There's a few things we haven't taught yet, so we only introduced the idea here. So do know that if you're reading general chemistry materials in general, you may see much more complicated titration questions, and that's not because you missed something that you were supposed to learn. It's not like, oh my gosh, I didn't realize I'm supposed to be able to do all these other things. We are just using it to find the concentration of acids and bases, and that's all we're doing with it for now. We will do a lot more with it in 1212, but this is a good starting point. And that means you get to build on it later. So this stuff isn't just going to disappear. You will use these ideas, and then we'll build more on top of them. So hopefully that works out. So this is how we can find out the concentration of an acid or base without having to react to all of it. So as you might imagine, I didn't want to have to react the entire lake. I just want to pull a little sample out, and that tells me the concentration of the entire lake now. Since whatever concentration the little container had, it's going to be the same for my lake overall, since we're assuming it's reasonable that the acid is equally spread out. So to know how concentrated a tiny bit is, that's how concentrated the whole lake would be as well.